path coordinates. We will start from the very basics. So, in path coordinates, what we assume is that the path or equation of the path of the particle is known. So, that means if a particle is travelling along some path, so this path and its equations with respect to some coordinates x, y, z, these equation of the path is known. So, what we do here is, first of all, we choose some reference point on the path, which is the initial point. It may be the point where the particle starts or somewhere along the path, and we will say this is the position where the particle is at time t is equal to 0. And then what we measure? We measure the distance travelled by the particle as a function of time. So, the distance travelled by the particle we use a symbol s for that. So, the distance travelled by the particle is s, and from this point we measure s as a function of time. So, this is the basic measurement which we do, and because the path is known, so therefore this has to travel along this curved path, we will keep on measuring s as at successive times. So, because I know s as a function of time, so that means I can also then find, we can find s dot, the rate of change of s with time, and s double dot, the rate of change of s dot with time. Now, what is the physical significance of s? S is the distance travelled along the path. What is s dot? S dot will be the speed of the particle, and this, as we know, will be equal to the magnitude of the velocity. And s double dot, this is, and this maybe we will use as, see now notice we will have two symbols, one is v without a vector and v with a vector. V with a vector denotes velocity, v without the vector sign is nothing but s dot is equal to the speed, and s double dot, this is the rate of change of speed, and this will be nothing but dv by dt. So, now if we go back to our basic picture and we have some coordinate system. So, the particle, now what we are saying is we are measuring s as a function of time. Now, if we have to find the velocity, then what we will do is, from the origin we mark the position vector at time t, we mark a position vector at time t plus delta t, and this is what we can call as delta r vector, which is equal to r at t plus delta t minus r at t. Okay. Now, if we look at and this distance, the distance travelled between time t and t plus delta t, we can call it as delta s, or in the limit delta t goes to 0, this will be ds. Okay. So now when we try to look at this, let us see first of all we can write ds square, that is the arc length, as dr dotted with dr. So as the time delta t goes to 0, the length of delta r vector will approach the value ds. It is a vector in a finite time. Dr, magnitude of dr is not equal to magnitude of ds, but as we move towards infinitesimal time with delta t going to 0, then the magnitude of dr vector will approach ds. So that I can write it as which I have written as ds square is equal to dr dotted with dr. Now what I can do is, and dr vector is nothing but equal to the vector p prime, where this is the point p, this is the point p prime. Point p is at r vector and p prime is at t plus delta t. So now once we have this, what I can write is, since we are measuring everything in terms of s, so ds square I can write it as dr by ds multiplied by ds. So all I am doing is, in this term, in each of these, I am taking, multiplying and dividing by ds. Now this can be written as dr by ds dotted with dr by ds multiplied by ds square, because the dot product is only between the vectors. The scalars can be taken outside the dot product, so therefore I do that. So this becomes dr by ds dotted with dr by ds times ds square, and from here what I get is, this gives me, this is equal to, or this is equal to magnitude of dr by ds whole square times ds square, and from here what I get is, this implies magnitude of dr by ds is equal to 1. Now what is this quantity dr by ds? Dr by ds, if we look at it, this is the rate of change of the position vector with respect to s. Okay. Now what is the direction of, what is the magnitude of dr by ds? We have just showed that the magnitude is 1. What is the direction of dr by ds? In terms of the path, what will be the direction of dr by ds? It will be tangent to the path. Okay. So now what we can do is, that means we can define a tangent vector as dr by ds, and this will be a unit vector because dr by ds is 1. So therefore we have defined now a unit tangent vector. So given these path coordinates, so that means we can define a unit vector which I will term as Et, which is equal to dr by ds, and what we show is that Et is in the direction of tangent to the path at the point. So what we have done here is, we have defined Et is equal to dr by ds, and this is equal to limit delta is going to 0 delta r by delta s. So this is a unit tangent vector in the direction of increasing s. Now, as the point P moves, the direction of ET will change if the path is curved. If the path is a straight line, its direction will not change, but otherwise in general the direction of ET will change. Now, let us look at this quantity. What is ET dotted with ET? ET is not constant, but its magnitude is. So, ET dotted with ET is always 1. So, what this implies is, if I look at d by ds of ET dotted with ET, what will this be? This will be 0, and this is nothing but 2 times det by ds dotted with ET. Therefore, what we have is det by ds dotted with ET is equal to 0. So, therefore, what we can do is, what we know, what this tells us is that det by ds is perpendicular to ET. We had seen a similar argument in the last class, where I talked of a general vector A, and this is exactly the same argument. So, what I show here is that det by ds is perpendicular to ET. So, now what we do is, we say a unit vector in the direction of det by ds is defined as the principal normal vector En. Let me first do some definition and then we come to the physical meaning of this. The magnitude of det by ds is defined as 1 over rho, where rho is called the radius of curvature. So, from the fact that I got that det by ds is perpendicular to ET, now there can be infinite perpendicular directions to ET. We choose the one which is parallel to basically det by ds, and that direction which is along det by ds, a unit vector along that, first we define that as the principal normal vector En. Now, the magnitude of det by ds will not be 1 in general. We showed that the magnitude of dr by ds, that was 1, but magnitude of det by ds will not be 1, and this magnitude we define as 1 over rho, where rho is called the radius of curvature. See, you see it from here also, det by ds, when you look at it, then the dimensionally s has dimensions of length. So, therefore, when you write det by ds is equal to, is parallel to En, that is how we have defined, and the magnitude we write it as 1 over rho, that you can say is a constant of proportionality. So, rho is termed as the radius of curvature. Again, this is all definition. Now, if the path of the particle is planar, if the particle is travelling along a plane path, it is not along a 3-dimensional path, then what we have is Et and En are along the path along the plane of the path of the particle. So, if this is a planar path, then Et and En will be along the same plane, and En which we said. So, now this plane, there is a term for this, this is called the osculating plane. You may have seen it in your maths, or you may not have seen. Even if you have not seen it, does not matter. This is just a name given to this. And in a 3D path, the osculating plane is the plane formed by Et at S and Et at S plus delta S, which actually means En, because En is dEt by ds. So, if you look at the plane containing Et at S and Et at S plus delta S, that will be the plane which will contain En at that time. So, that is, and the difference is, in a two-dimensional path, the osculating plane stays the same, whereas in a three-dimensional path, the osculating plane will keep on changing. At each instant, the plane will be the one containing Et at instant there and at the next instant. So, this is now what we have is, if we look at the vector Et, let me come back to this picture, or maybe I will draw it separately. Let me draw a new picture. Suppose if this is the path, I am blowing up, this is the point P, this is the point P prime. The vector Et here will be like this. This will be the vector Et at S plus delta S. So, now if I draw these two vectors together, this is the vector Et and this is the vector Et at S plus delta S. So, now the difference between these two, this is the vector delta Et, and this direction which I show by red, this gives the direction of the En vector perpendicular to Et. So, what we can say is that the direction of delta Et is perpendicular to Et, and delta Et, this points towards the center of curvature of the path. Now, we have just defined Et and En and this radius of curvature in a totally mathematical way. What is the physical significance of radius of curvature? If we make a circle, if we assume that the particle is traveling in a circle between P and P prime, if we join it by a circular arc, then the radius of that arc will be the radius of curvature, and the dEt by ds has to point towards the center of curvature. It cannot point away. We have made that as a part of our definition, because dEt by ds, if we will have to look at perpendicular to this, there could be this direction or there could be this direction, and we choose the direction which is towards the center of curvature. So, physically, what this means is, if the point P was traveling in a circular path at that instant, rho would be the radius of the circle. So, that means now we have defined a vector E t and E n. We have defined two unit vectors like this. So, now we can define a third unit vector which can be taken as E t cross E n, and we will call this as E b, the binormal unit vector. So, what we have is a triad of vectors E t, E n, E b, and these form the path coordinates. Let us once again, if we look at the path coordinates, so what we have is dr by ds, this gives us the vector E t, and det by ds, which is nothing but d2r by ds square, this is equal to 1 over rho E n, and then we have E t cross E n is equal to E b, E n cross E b is equal to E t, and E b cross E t is equal to E n. Now, let us look at this definition. E t cross E n is equal to E b. Let us take magnitudes of both sides. So, magnitude of E b is equal to magnitude of E t cross E n. Okay. Now, what is E t? E t is dr by ds. And what is E n? E n is rho times d2r by ds square. Now, what is magnitude of E b? 1. So, therefore, what I get is, now this rho is a scalar. So, I can pull this out also. So, what I will get is that rho is equal to, or 1 over rho. So, from here, since magnitude of E b is equal to 1, so from here what I get is 1 over rho is equal to dr by ds cross d2r by ds square. And this is the basic formula I will use in trying to find out the radius of curvature rho, that dr by ds cross d2r by ds square is what gives me rho. What we have also seen at the cost of repetition, I will say the plane of E t and E n, this is what we have called as the osculating plane. Now, let us see the path coordinates. Let us work out, and these expressions then turn out to be very simple. Let us work out what is the velocity. So, the velocity in path coordinates, we will write it, velocity we know is nothing but dr by dt. So, now if I have to convert things in path coordinates, I have to write it in terms of s, that is the variable. So, I will write it as dr by ds times ds by dt. What is ds by dt is s dot. What is dr by ds? This is nothing but the tangent vector E t. So, what we get is, this becomes just a one line thing, that velocity in path coordinates is equal to s dot E t. Does it make sense? What is s dot? The magnitude of velocity, the speed. What is the direction of the velocity? Tangent to the path. It cannot be anything else. So, therefore, physically it makes perfect sense that velocity is equal to s dot E t along the tangent with the magnitude of equal to speed, straightforward. Now, let us take one more step further. What is acceleration? acceleration is dv by dt. So, let us go to this. So, is equal to d by dt of s dot et. So, first I will write it as s double dot et plus s dot times det by dt. So, now this second term I will write it as s dot det by ds times ds by dt. Okay. So, what is ds by dt is nothing but s dot square. What is det by ds? It is 1 over rho En. So, this becomes 1 over rho En. So, when you combine all this together, you get acceleration is equal to s double dot et plus s dot square upon rho En, or s double dot et plus v square upon rho En. So, this is the simple formula for acceleration in path coordinates. What do we get to know here? In path coordinates, if we know the path and t is the tangent to the path and is normal to the path, then acceleration has got two components. The first component is along the tangent, which is equal to the rate of change of speed. If the speed is not changing, then this component will be 0, and this is along the tangential path. But in addition to that, even if the speed is not changing, we have a component of acceleration which is normal to the path, which is equal to the speed square divided by rho, where rho is the radius of curvature along En. So, it is pointed towards the center of curvature of the path, and its magnitude is v square upon rho. So, even if v is constant, we will have a term. When will this term? So, for this term to exist, there are two things. One is v has to be non-zero, and the other thing is that rho has to exist, which means that it has to be a curved path. If it is a straight path, then rho will be infinity. We will show that in a formula. So, therefore, we have this term, and actually if you think about it, this is something which we probably know. If we look at things in a circular path, that is right, and we place the origin at the center, then what do we know? The velocity is r omega. In which direction? In the tangential direction. So, that is equal to s dot. S dot is nothing, r theta, s is r theta. So, you take its derivative, you will get r is constant, so r theta dot, which is r omega. And acceleration, there are two components, one is r alpha and the other is minus r theta dot square, and En actually is minus of Er if you place things at the center. So, therefore, this is some. Now, this looks like a very simple formula, but actually this formula will turn out very handy. Often when you have, and particularly when you are talking of multiple frames, what you have to look at is, with respect to one frame, what is the path of the coordinate, path of the particle, and then once you know the path of the particle, then all you can do is you can say s double dot et plus v square is along et, along En it is v square upon rho, and we will use it many times. So, wherever if you are getting a bit confused in a curved path, think of path coordinates and can you find the radius of curvature. Essentially, if you have to use path coordinates, the main thing will be how do you find rho. If it is a circular path, then rho is quite straightforward. It is just the radius of the path. If it is not, we will see how to find that. Do you know if something is travelling along a path y is equal to fx, is curvature related to some derivative? You must have done it in your basic calculus course. It is related to the second derivative. Basically, this will be something related to the second derivative, and we will come to that. We will show it to you in a moment. Okay. So, now let me write some comments about these formulas. We have already said this, that what we find here is that v has got only one component, et. By definition of path coordinates, velocity cannot have a second component. because velocity has to be tangent to the path. If it is not, that means the path will change. It is just going inside the path. Okay, so it has to be by definition tangent to the path, nothing else. So we have defined the coordinates in such a way. So that means along this, so Vt is not equal to 0 and Vn and Vb, both of these components are equal to 0. Secondly, we realize, and this is not very physically obvious, that acceleration has only two components, An and At. An is not equal to 0, At is not equal to 0, but the binormal component of acceleration has to be 0. And also we realize At is just the rate of change of speed, An is equal to V square by rho. So change in magnitude of speed, this causes At, and the change in the direction of speed, this is what gives birth to the An component. And the other thing we realize from this formula is that An has to be greater than or equal to 0. So that means An always points towards center of curvature. So therefore, some possible sort of configurations of accelerations are ruled out. If you get an acceleration component such that normal is pointing away from the center of curvature, that is not possible. We cannot have it like this. Acceleration, if there is a normal component, it always has to point towards center of curvature. So sometimes these are problems you will get often in objective type questions. You will have some direction of acceleration. If you look at the normal component of that, if it is pointing away from the center of curvature, that is not possible. That configuration of acceleration is not possible. Okay. Now other thing we realize is, because An is equal to V square upon rho, if rho is small, what will happen to An? An will become very large. So these sort of things you have to keep in mind when you design things, because suddenly if you have a path where the radius of curvature becomes very small, then accelerations will become very large, the normal component of acceleration. And why are we so interested in accelerations? We know accelerations are directly proportional to the forces. So that means if the acceleration becomes very large, the force encountered by the body will become very large. So therefore, while designing things, often things that we have to take care of things that An is not very large. That means rho has to be reasonably big. We don't make things with very small radius of curvature. Okay. So now how do we work out rho? Let's have a look at this, and I'll give it a general go. I don't think this is given in the book. So let's see. Let us look at, if the trajectory of the particle is known in terms of its position vector r, and position vector r is a function of any variable tau. It could be time. I could know, if I know position vector r as a function of time, then obviously I'll know the trajectory. But instead of time, maybe I know r as a function of, let's say, x coordinate or y coordinate, any one coordinate, or some other variable. It could be something else. When we talk of various coordinates, it could be a function of theta. So r is a function of tau, which could be any variable. We know the position as a function of some variable, which could be either x, y, z or something else, time or s, anything like this. So now what because r is known as a function of tau, let's work out Et vector was given as dr by ds. So magnitude of Et is equal to magnitude of dr by ds, and this I can write it now because I know things in terms of this new parameter tau. So I could say tau is any variable, or in mathematical terms we call it as a parameter. So this I can write it as magnitude of dr by d tau into magnitude of d tau by ds, and because magnitude of Et is equal to 1, what we get is that whatever this variable tau is, its relation with s will be 1 over dr by d tau. So I am just relating everything to s, the path variable, because in path coordinates I am working in terms of s. So I know r in terms of tau. So first of all I find what is dr by d tau in terms of d tau by ds. So now, having done this, let's just look at this. Now we had derived a formula. I want to find the value of rho. We said 1 over rho was dr by ds cross d2r by ds square. This was for a general path. We have derived this. We just showed by taking magnitude of EB was 1. We got this. So now what we will do is, let us work out dr by ds in terms of tau, because r is known in terms of tau. So what we have is dr by ds, this is equal to dr by d tau times d tau by ds, and d2r by ds square, this will be equal to, first I differentiate d2r by d tau square into d tau by ds whole square plus dr by d tau times, all I am doing is I want to find out dr by ds cross d2r by ds square. I know r as a function of tau. So first I write dr by ds as dr by d tau times d tau by ds. The second thing, I take another derivative of this. So dr by d tau, when I differentiate this, first I will get d2r by d tau square times d tau by ds multiplied by this, plus dr by d tau comes as it is, and derivative of this with respect to s, so d2 tau by ds square. This is standard now, we have been doing this for many things. Now let us take a cross product of these two. So from here, let us take dr by ds cross d2r by ds square and its magnitude. So now in this you realize dr by d tau is the vector part, d tau by ds and all are scalars. So now when I take a cross product of these two, I will get something which is non-zero. When I take a cross product of dr by d tau with the second term, then I have a dr by d tau crossed with dr by d tau. So that will be 0, because everything else is a scalar. So therefore, when I look at this, what I get from here is magnitude of dr by ds cross d2r by ds square. This will be the magnitude of dr by d tau cross d2r by d tau square times d tau by ds whole cube. So basically I will get only the first two terms. Okay. Now d tau by ds, so this becomes equal to magnitude of dr by d tau cross d2r by d tau square divided by, now we had shown that d tau by ds here was 1 over dr by d tau. So that means we use this and this becomes equal to divided by dr by d tau whole cube. So this is equal to 1 over rho. So this becomes the general formula for finding the radius of curvature, where I know r as a function of any variable tau. I have sort of, you look at it, what I have done is converted everywhere, wherever tau was first in terms of s, and then later on put everything back in terms of tau, because I knew r as a function of tau. Okay. So now this is one formula. You again, as I told you, you don't have to remember these formulas, they will be all given to you in the exam. If these formulas are needed, they will be given to you. But now let us see, tau is any variable. What happens if tau is t? What is dr by dt? Velocity. What is d2r by dt square? Acceleration. So if tau is equal to t, what we get is 1 over rho becomes, so from here now we can derive different formulas for radius of curvature. So if tau is equal to t, then this implies 1 over rho will be equal to magnitude of v cross a divided by magnitude of v cube. So this tells you at any point when a particle is traveling, if you know the velocity vector, not the scalar, and if you know the acceleration vector, then v cross a divided by magnitude of v cube will give you 1 over rho. So you can find radius of curvature using this method. There is another thing we have already shown how we can, so these are various ways of finding radius of curvatures. If you know the normal component of acceleration and if you know the speed, can you find the radius of curvature? An is equal to v square by rho. So suppose if you know the normal component of acceleration, then you can obviously find the radius of curvature. Okay. Now given this, now comes the, suppose if we know, and this becomes the last part in the formula to be done, if there is a planar trajectory, we have a particle which is traveling along a plane and this path is given by y is equal to fx. The particle is at a point P which is xy. So we have a trajectory y is equal to fx. Now notice how I will approach this, because this is the basic way. If we have to find the radius of curvature here in terms of derivatives of y, then what I have to do is, I know the path in terms of x. I have to use the formula 1 over rho is equal to dr by d tau cross d2r by d tau square divided by dr by d tau whole cube. Now let us see, that is the basic formula. So let us write first of all the r vector. This is equal to xi plus yj, and this I can write it as xi plus f of xj. So that means now if I look at my formula, what is tau here? Tau is x, because I know the path in terms of the variable x, and this is what you should be able to derive or you should be able to think of. So here that means in bracket I am writing tau is equal to x. So now what I have to do is, if I have to find rho, I have to find dr d vector r by dx, d2 vector r by dx square, and that's it. I am done, isn't it? So let's do that. So now d vector r by dx is what? Derivative of xi. How, when I differentiate it with respect to x, what do I get? I plus, I differentiate this with respect to x, I will get f prime of x j, because I and j these are fixed coordinates, so that's what we have. And second thing, now let's find differentiate it with respect to x once more. What's the derivative of I? 0. Second term, f double dash x j, that's it. So now I have to use my formula. The magnitude of dr by d tau, that is dr by dx, cross d2r by d tau square, which is d2r by dx square in this case. This will be equal to, let's take a cross product, I cross j, that's the only term which I will get, j cross j will give me 0. So this will be nothing but equal to magnitude of f double prime. And we have to now also find the magnitude of dr by d tau, that is magnitude of dr by dx. What is that? This will be equal to square root of, what the coefficient of I? 1. So square root of 1 square plus f prime x square. So this is equal to root of 1 plus f prime square. And from here what I get is 1 over rho is equal to magnitude of f double prime divided by square root of 1 plus f prime square whole cube. So this I can write it as magnitude of f double prime divided by 1 plus f prime square to the power of 3 by 2. So this is the formula which I derive when I have to find y as a function of x, when I have to find the radius of curvature if I know y is equal to fx. So I will use magnitude of f double prime divided by 1 plus f prime square to the power 3 by 2. This is for a general path. Otherwise, if it's a circular path, then you clearly know it is nothing but the radius. Okay. So this is the formula. Now, if we are at this general point P, how do you find the vector ET and EN? See, you should also be able to find this. So now, suppose if I look at this tangent, I should choose, let me take another point P which is slightly at a better place, so that I should be, so if this is the path, this is the point, so I'll choose not this one, I'll choose it at a slightly higher gradient so that I can draw the figure properly. If this is the point P, then if I draw the tangent to point P, if this makes an angle psi with the x axis. Okay. So now if I look at this, dy by dx at point P, this is equal to tangent of psi, and this is nothing but f prime. So ET vector, I can write it as cosine psi I plus sin psi j. So first step in finding the vector ET will be to find dy by dx, then you will know the angle psi, tan inverse of that, and then cosine psi I plus sin psi j will give you ET. Now det by ds, this will be equal to minus sin psi I plus cosine psi j times d psi by ds. So now En vector will be det by ds divided by magnitude of det by ds. So this will be equal to, sorry, this minus sign I have put it as outside the bracket. Minus sin psi I plus cos psi j, so bracket should be outside here. So this will be equal to minus of sin psi I plus cos psi j times d psi by ds divided by magnitude of d psi by ds. And this quantity which I have, this will be either plus 1 or minus 1. Anything divided by its magnitude will be either plus 1 or minus 1. So, En vector which we have is perpendicular, and so now what we have is, as I told you, the best way to find En vector, if Et vector is cos psi I plus sin psi j, then En vector, if it is along the same plane, means what? It is perpendicular. So, therefore, what will happen is the I component will have the sin psi and the j component will have cos psi. Now, either there will be one of these will be negative. Which one of these is negative? You will see it which is facing towards the center of curvature. So, in this case, the curvature is like this. That means the I component is positive and the j component is negative. So, you will get physically, you have cos psi I plus sin psi j, this will be sin psi and cos psi. So, then you look at the direction of the towards center of curvature, you find that the j component is negative, the I component will be positive. There could be a possibility when Et has got both of them as negative. If that is so, even then in En it will be one of them will be positive, the other will be negative, and also you see after you have finished, you look at Et dotted with En, then you get cos psi sin psi minus sin psi cos psi, which is 0. So, Et dotted with En should always be 0. So, that way you will make sure you will not have made any mistake. Okay. So, basically this is just the theory of path coordinates. So, in fact, if I can just complete this, that if this basically it will be minus sin psi I plus cos psi j multiplied by either plus 1 or minus 1, and that is determined by the direction towards center of curvature, not away. So, with this you can basically solve any problems involving get this thing, but so the example let us take is one of path coordinates. Suppose we are given that a particle is moving along a path where y is given as 1.22 times square root of x. The particle is at a position A where x coordinate of A is 1.5 meters. Now, it is given that speed at A is equal to 3 meters per second, which is changing at the rate of plus 3 meters per second square, and we have to find the velocity and acceleration in terms of I and j. Okay. So, this is the problem. Now, S dot is given, S double dot is given, and the curve is given. So, now if we want to find the speed or the velocity, so first of all velocity will be equal to S dot Et, which is equal to 3 Et. So, the first thing we have to do here is find Et. So, Et we can write it as equal to cos alpha I plus sin alpha j, where tangent of alpha is equal to dy by dx. So, we do not need to draw this, but notionally what we are doing is we are calling what I called psi, I call this angle as alpha. So, tangent alpha is equal to dy by dx. So this will be equal to 0.610 divided by root of x. So at x is equal to 1.5, what you will find is tangent alpha is equal to half. That is what when you work out. So this implies alpha turns out to be equal to 26.5 degrees. So ET vector is equal to 0.895 I plus 0.446 J. So once I have alpha, I work out ET vector. So the answer for velocity is already, I have got this. Now the next thing would be to work out En. Yes. No, because it's well, that probably will be specified to you. It's given that the particle is moving like this. So that is given to you. Okay. I should have specified that. Okay. Now En vector. Now Et is cos alpha I plus sin alpha j. So En vector will be sin alpha I cos alpha j, and if I look at this picture, I know En has to be something like this. If this is Et, so therefore I will have plus sin alpha I minus cos alpha j. So En vector is equal to 0.446 I minus 0.895 j. Once I have done this, so then all what I need to know is acceleration is equal to s double dot Et, which now I know fully, plus s dot square upon rho En. So I know s dot. Only thing now I need to find out is find rho. And how do I find rho? I will use the formula. So now for finding rho, I get dy by dx is equal to 0.610 over root of x, and d2y by dx square, I take a second derivative. This is 0.305 minus of this divided by square root of x cube, so x to the power of 3 by 2. So now rho is equal to 1 plus f prime square to the power of 3 by 2 divided by magnitude of f double prime. So I have everything. I put x is equal to 1.5. I calculate the value of rho. You do it at home. So take 1 plus this quantity, put x is equal to 1.5 square divided by, put x is equal to 1.5 again, take it to the power whatever, and then work out. So you get rho, and once you get this, then all you have to do is get A in terms of I and j. You will just have to plug in values. I am sure you will be able to work out. Is that clear? Are there any questions on this? The how to find the acceleration vector or acceleration values. Okay. So this is how one can work out some things. Now let me take another example of cylindrical coordinates. We had done cylindrical coordinates last time. Let's take example 2. And this is to show you that actually cylindrical coordinates are very easy. All you have to do in these problems is to work out what is r, theta and z. So here I have a wheel with threaded hub, rotates at 80 rpm on a right hand screw with pitch 100 mm. At this instant, rate of change of angular speed is equal to 20 rpm per second. I will draw the figure also. A sleeve A advances along the spoke. I will draw the figure, then this will become clear. At a speed of 2 meters per second and increasing at the rate of 1 meter per second square towards the center of the wheel. At this instant, the sleeve is 0.5 meters. Don't need to write this down, I'll put this on the web, so you'll have this. You can just probably, it's at 0.5 meters from the center. And again we have to find the velocity and acceleration. So let me first draw the picture. We have a wheel like this. There are some spokes on the wheel. Now this wheel is on a threaded screw. So that means the wheel is rotating. So the rotation of the wheel, the angular velocity and angular acceleration of the wheel are given to you. We'll see how to work that out. But while the wheel rotates, it is also coming out of the page of the plane of the board. Why? Because this is a right-handed screw. So as you rotate, it also comes out. And this distance, so now here what we are doing is, what we have been told is that there is a spoke here. Let us say this is the spoke. At this instant, this is 0.5 meters from here, and it is moving toward the center of the wheel with the velocity equal to 2 meters per second and acceleration equal to 1 meter per second square. Okay. So if you look at the total wheel, the wheel is undergoing a motion in the circular direction. As it is moving in the circular direction, it is also coming out of the board, and that relation is given by the pitch. What the meaning of pitch? The distance it comes out along Z in one revolution. So I'll just put that in terms of maths. And also there is a spoke here, and on this spoke there is something which is moving towards the center of the wheel. So these are the three motions taking place. So what we do is, at this instant, let us say we will call this as the R direction, theta direction will be in this plane, and Z, so ER at this instant is here, E theta is perpendicular, and EZ is coming out of the board. So now to solve this problem, let us first work out what is R. R is given at this instant equal to 0.5 meters. Okay. Now in our formula we need R dot and R double dot. What is the rate at which R is changing? What is R dot? Minus 2 meters per second. So R dot is equal to minus 2 meters per second. What is R double dot? It is equal to minus 1 meters per second square. Again it is moving towards the center, so therefore this is minus 1 meters per second square. Now theta actual value we don't need. What is theta dot? Theta dot is this omega. So this is given as 80 rpm. So this will be, let us just see how to convert this, 80 into 2 pi by 60 radians per second. So this is theta dot. Is that clear? Theta double dot is 20 rpm per second. So 20 into 2 pi by 60 radians per second square. This is the rate at which theta is changing, theta dot is changing. Okay. Now Z is the distance this is coming out. What is Z? Z is equal to pitch into theta upon 2 pi, because when theta is equal to 2 pi, it comes out by 1 pitch. Okay. So Z is equal to P multiplied by theta upon 2 pi. So this we can write it, what is pitch is given to us, we have to be careful with the units, is equal to 0.1 theta upon 2 pi. So what will be Z dot? Z dot will be 0.1 theta dot upon 2 pi, and Z double dot will be 0.1 theta double dot upon 2 pi, where theta dot and theta double dot have already been worked out. So now once you have worked out all this, your answer is just plugging everything in the formula. You don't have to do anything else. In cylindrical coordinate, that's the advantage. Once you visualize the problem and you work out what is your r, what is your theta, what is your z, and you find the appropriate expressions for r, theta and z, then the problem is just solved. Then all you have to do is velocity will be equal to r dot er plus r theta dot e theta, and acceleration is equal to r double dot minus r theta dot square er plus 2 r dot theta dot plus r theta double dot e theta plus z double dot ez. So all you have to now do is plug everything in the formula and get your answers. So that's how cylindrical coordinates makes life slightly easy. Okay, I think I'll end the class here.